8.1 Sequences and Series. Well, we should learn how to use a sequence notation to write terms of sequences, use factorial notation, use summation notation to write sums, find the sum of an infinite series, and use sequence in real life problems. Sequence in math and sequence in English is kind of the same thing. It's just a list of numbers, a list of things, I should say. Right, so we have a first member, a second member, like you see here. Here's our infinite sequence. We have A1, A2, A3, A4, all on AN, all on forever. So it's kind of like a function, but instead of writing in a function notation, we just write it with increasing terms. So if a sequence ends, like if AN was our last term, that's called a finite sequence. When it goes on forever, it's called an infinite sequence. So here's our first sequences. Write the first 4 terms of each sequence. So a sequence always starts with A1. So a sequence always starts with n equals 1, 2, 3, and so on. So now we don't start at 0, we don't start at -1, it always starts at 1. That's our sequence. So our first term here is going to be 3 times 1 minus 2, also known as 3 minus 2, which is 1. A2, 3 times 2 minus 2, so 6 minus 2, which is 4. A3, 3 times 3 minus 2, 9 minus 2, which is 7. And then A4, 3 times 4 minus 2. Now this one, you don't have to do the math. If you notice, all we're doing is adding 3 every single time. So look at it's been 10. So that's our first sequence. 1, 4, 7, 10. This one right here, so a slightly different sequence, but we're doing the same thing. 3 plus -1 to the first. Well, that's 3 plus -1, so just 2. A2 is 3 plus -1 squared. Now when you square a negative, you actually get a positive. So you have 3 plus 1, that's 4. A3 is 3 plus -1 cubed. Odd power keeps it negative, so we're going to get 3 plus -1, which is 2 again. And A4, 3 plus -1 to the 4th. Even power makes it positive again, so we get 4. So the sequences keep on going 2, 4, 2, 4 until the end of time. So that's how you write the first few terms of sequence. You just plug in 1, 2, 3, 4 until you're done. This will be the first 5. We're going to skip this one because it's more of the same, but plug in the first 5 terms. Okay, write an expression for the parent ninth term, mth term of a sequence. So we want the formula basic. So sometimes these be kind of tough because you're trying to like figure out, well, how do I plug in 1 to get 1? How do I plug in 2 to get 3? And plug in 3 to get 5? Now, like that's the idea here. So for A, we're going to plug in 1, we should get 1. Should plug in 2 and get 3. Plug in 3 and get 5. Plug in 4 and get 7. Right? So, if we notice, we're adding 2 every single time. It's linear, right? It's changing by a constant number, 2. So, in that case, we could try to treat like a linear equation, mx plus b. Now, our m is our slope, which is constantly changing every single time. In this case, 2. B is our y-intercept. Now, it's a little tricky. It's not 1 because 1 is at 1. If there was the 0, what would the 0 be? Is essentially what the y-intercept is. Right? Where would we start off if we start at 0? You know, when we do a sequence, we start at 1. Well, if you're going plus 2 everywhere, minus 2 to go back, so be at -1. So that should be our b. Our formula should essentially be 2n minus 1. And we could check if that works. If I plug in 4, do I get 7? And yes, we do. Right? If I plug in 1, I get 2 minus 1 is 1. So that is our formula. So if we notice it's increased by a constant amount, that's a linear function. We can treat it like a linear function. This one is not increasing by a constant amount. It goes from 2 to 5 is 3. Then 5 to 10 is plus 5. And then plus 7. So it's a lot harder to come up with the formula for because it's not linear. So sometimes you just gotta think, okay, what do I do? What could I do to 1 to make 2? What could I do to 2 to make 5? What could I do to 3 to make 10? And 4 to make 17. Now, so sometimes you want to, could I multiply by a number? If I multiply them all by 2, like 1 by 2 gets me 2. 2 by 2 gets me 4, which is just plus 1. That's not going to help. What if we square them? 1 squared is 1. I'm 1 away, so you could add 1 to that. So we could do this. How about that? Right, 1 squared is 1, but I'm 1 away from 2, so plus 1. 2 squared is 4, plus 1. 3 squared is 9, plus 1. 4 squared is 16, plus 1. So that's the formula for that one. Again, there's no real trick to it. You just kind of gotta look at it and try to figure out what's going on there. Just keep in mind it always goes 1, 2, 3, 4. So one has to get to the first. You have to plug in 1 to get the first one, plug in 2 to get the second, 3, and so on. Sometimes they give you a recursive function. Recursive function means it uses the answers before it. So like here, a1 equals 3, ak equals 2 times ak minus 1 plus 1. So we have to write the first 5 terms. So all this means is if you want the next term, you're going to use a term before it. So a1 we know is 3. If I want a2 using the formula, you can plug in 2 here, in here. Let me erase this. And you're going to get a2 equals 2 times a2 minus 1 plus 1, which is the same thing as saying a2 equals 2 times a1 plus 1. So it's always going to be the one before. That's what this k minus 1 means, the previous term. So in this case, it's just a1 plus 3. But we know what a1 is. 3. Plus 1, sorry. So we get 3 plus 1 is 4. Now if I want a3, it's going to be the term before it, a2 plus 1. Well, this is 4. 4 plus 1 is 5. And then a4 would be a3 plus 1. And this is 5, so 6. So that's a recursive. Oh, I guess I want a5. That's a recursive formula though. Right, so you can use the one before it. In this case, it's 6, so we get 7. So that's how you do a recursive formula. The Fibonacci sequence. This is like a famous special recursive formula you see all the time in nature. So it actually uses the 2 before it. See how it says ak minus 2, ak minus 1? So this is a term before it. This is 2 terms before it. So we start with a0, and that's 1. a1 is 1 also. a2 would be the term before it, a1, plus the term before that, a0. Right, basically just adding the 2 terms before. So this is 1 plus 1, which is 2. So a3 would be the term before it, a2, plus the term before that, a1. So we're just adding 2 plus 1 is 3. And that's how it keeps on going. The Fibonacci sequence, you're just going to add the 2 terms before. So 3 plus 2 is 5. a5 would be 5 plus 3, which is 8. a6 would be 8 plus 5, which is 13. You can keep on going. That's a Fibonacci sequence. You just keep on adding the terms before it. And it's a famous one you see all the time in nature. It's kind of like why 4-leaf clovers are so like lucky, because you generally see a 3-leaf, a 5-leaf, or 8-leaf clover. You never see a 4-leaf clover because it doesn't follow. In nature, you generally follow rules like Fibonacci sequence. Factorial notation. So factorial is just a notation which means multiply all the numbers beneath that number. So if I give you like 3 factorial, all that means is multiply everything beneath it. 3 times 2 times 1. We stop at 1, like all the natural numbers. So we get 6. Right? By definition though, keep in mind 0 factorial is 1. It has to do with probability. How many ways can you rearrange 0 things? We say 1. There's only one way to rearrange 0 things. So that's how factorials work. You just multiply everything beneath it. If you see like 10 factorial, 10 times 9 times 8 times 7 6, you get really big really fast. That's all factorial. 4 factorial is 1 times 2 times 3 times 4, and so on. Write the first 5 terms of the sequence given by this guy. So we just want to see, let's practice some factorial. So a1 would be 2 to the first 1 factorial. So this is just 2. 1 factorial is just 1, so we get 2. a2 is 2 squared times 2 factorial. So that's 4 on top, 2 times 1 on the bottom. So 4 over 2, which happens to be 2 again. a3, 2 to the third times 3 factorial. So 2 to the third is 8. 3 factorial is 3 times 2 times 1. So that's 6. So 4 thirds. a4, that's 2 to the 4th over 4 factorial. 2 to the 4th is 16. 4 factorial, well, it's just going to be this answer here, 6 times 4. Right, because it's all factorial is. You're multiplying 3 times 2 times 1. Well, I already know that's 6, so times that by 4. So 24. And we can reduce that by 8, and you get 2 thirds. I guess we do a5, last one. 2 to the 5th over 5 factorial. So 2 to the 5th is 32. 5 factorial, again, it's just 1, 2, 3, 4, but that is, 5 factorial is just 4 factorial times 5. Right, it's just multiplying everything up. So this is 24 times 5 is 120, and then you can reduce that. I'm going to leave it like that though. Simplify factorial. So there's actually a shortcut to this. So you see here you have 8 factorial over 2 times 6 factorial. The shortcut to this is we could break up 8 factorial to this. 8 factorial is the same thing as saying 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But all of this is just 6 factorial. So the way you want to break it up is actually like this. You're going to break 8 factorial, you're going to say 8 times 7, and then you're going to stop at 6 factorial. Because that way we know that 6 factorial is going to cancel with that 6. So that's the way we simplify it. We go get the bigger number, break it down till you get to the next bigger number, and then you stop. On the bottom here, we could break down 2 times 1, and then we're going to leave the 6 alone because that's going to cancel out. So these cancel. We have 8 times 7 over 2. I could reduce the 2 and the 8, and I get 4 times 7 is 28. Just like that. So just real quickly, let's do another one to make sure we get it. So if I gave you, I don't know, 7 factorial over 4 factorial, 3 factorial, right? 7, I'll go 7 times 6 times 5 times 4. That's where I'll stop. I'm not going to do anything to the 4 because I know it's going to cancel. The 3 I do want to reduce. Some would say 3 times 2 times 1. That's what 3 factorial is. Then look what cancels. 3 times 2 is 6, but that's going to cancel with that 6. I just get 7 times 5, 35. That's how we reduce factorials if we have fractions. And we want to do the same thing here, the same concept. What's n factorial? Well, n factorial is n times the number before that, which is n minus 1, times the number before that, n minus 2. And you keep on going until you get to 1. That's how factorial works. So here, if I just stop at the 1 right there, that's going to cancel out with this one. So we're going to do that. N times n minus 1 factorial over n minus 1 factorial. These cancel. You just get n. So that's how you simplify factorials. Summation notation. So this is a notation. That's all it is. And really, every time you see this, it just means sum up all the values. That's it. So it's like a sequence, but then this thing tells you to add them up. Add. This is where you start your sequence. This is where you're going to end the sequence. And that's all it is. If I'm doing a problem and I see this E there, I'm like, oh, they want me to add up all these values. So we're going to start at 1, plug it in, and then until you get to 5, and then you stop. And then you add them all up. So that's all this is. So we're going to start at 1. So at 1, I'm going to get 3 times 1, which is 3. Then at 2, 3 times 2, which is 6. 3 times 3, which is 9. 4, 3 times 4, 12. And then 5, 3 times 5 is 15. Now again, I started at 1 because I started here because of that guy. And I ended here because of that guy. And the formula I was using was because of this guy. Right? The reason I was using this is because of that. So the only thing left is what did I do with the E? The E means add them up. So we're going to add all these up. So 3 plus 3 is 9. And then 9 plus 9 is 18. 18 plus 12 is 30. 35, 45. So you just add all those up. So it's kind of like that was going to be 18. 18 plus 12 was 30. 30 plus 15 was 45. That's how you do stuff. Now this one shows you that you don't need to start at 1. You can start anywhere. So in this case, we're going to start at 3. So this same idea, plug 3 in first. 1 plus 3 squared. That's 9 plus 1 is 10. 4. So 1 plus 4 squared. So 16 plus 1 is 17. 5. 1 plus 5 squared is 26. And then 6. 1 plus 6 squared is 37. And again, since we're doing a summation, because I see that E, we're going to add all these up, and we get 90. So that's the sum of all those. Here's some properties of sum. If you're just doing a constant, then it's just a constant times a number. You can always pull a constant out, so there's a formula of constant, you can pull it out to the front. You can also separate two sums, and you can subtract some two sums. Okay, let's talk about what series means. So a series is like a sequence, but you add it up. So like in a sequence, you're going to have A1, A2, A3, yada yada. In a series with the exact same values, we're just going to add them up. So it's A1 plus A2 plus A3, and so on. So that's what a series is. So if we want to use our summation notation to show it, a finite series is one that ends. So you just go 1 to n, right? So whatever we're going to start our first term, we're going to go to our nth term. That's what a series will look like. An infinite series means it goes on forever. So we're going to use infinity sign to show that. So it goes on forever. So let's look at this example here. Find the third partial sum and the sum. So the third partial sum of this means we're going to go up into 3. So 1 is going to be 3 over 10 to the first. So 3 over 10. 2 will be 3 over 10 squared, which is 3 over 100. Let's make this in decimals. That's 0.3. That's 0.03. 3 is going to be 3 over 10 cubed. So 3 over 1,000, which would be 0.003. If we add all these up, because we're doing summation for A, we're going to get 0.333. Now, what if I wanted the sum of all of that, like the whole thing, even though it goes to infinity? You can still find the sum when it goes to infinity. It's possible. If you look at here, all we're ever going to do is just get more and more 3's past it. So really, we're just going to get 0.3 with a line over it, which is the same thing as 1/3. So that's the sum of the whole thing, right? So you could find the sum of an infinity. If it just keeps on getting smaller and smaller, you actually could find the sum of it. So that's how infinite sum works. And that's the lesson.